Now, let us see the Archimedes principle. It states that whenever a body is partially or completely immersed in a fluid at rest, the fluid will exert pressure on the surface of body. A net force acts in the upward direction, which is called upthrust. Now, first of all, let us understand why the fluid exert any force. Whenever we keep or put the object in the liquid, this object will try to occupy some space within the liquid. To occupy the space, it will push the liquid molecules in all the direction and it will occupy some space. Whenever the liquid molecules are displaced, their interatomic force is changed. Now they are not at equilibrium. So to be in equilibrium, they'll again apply force in the opposite direction on the object to regain their original position. So like this, the pressure on the object and the force on the object is exerted due to the liquid. The net force acts in the upward direction. Let us find what is the value of this net force. Let us consider a cubical block of side A. When submerged in a fluid of density ρ, which is at rest, it experiences an upward force at the bottom and downward force at the top. Let's say it experiences upward force F2 and downward force F1. The downward force F1 is equals to P1A square, where P1 is the pressure at the top, and F2 is equals to P2A square, where P2 is the pressure at bottom. The net upward force is equals to F2 minus F1, that will be equal to P2 minus P1 into A square. But this pressure difference will be equal to rho G into A square. So rho G into A cube, but A cube is the volume of cube. So we can write the net upward force F2 minus F1 is equals to density into volume into G. The density is of liquid. The volume is the volume of cube. And this much amount of volume is displaced. So we can also write it is the volume of liquid displaced due to block. So this is density of liquid and this is volume of liquid. Density into volume can be written as mass into G. So net upward force is the mass of liquid displaced into G, that is equal to weight of liquid displaced. This net upward force is called buoyant force. So the Archimedes principle says that whenever a body is immersed partially or completely in a fluid, it experiences an upward force that is called thrust because it acts perpendicular to the surface of object. And that thrust is called buoyant force, which is equal to weight of the fluid displaced by it. So in short, the Archimedes principle is upthrust is equals to weight of fluid displaced. Due to this upthrust, the body will have lesser weight in given fluid compared to the air. Now let us see the principle of flotation. Whenever body is immersed fully or partially, there can be three different situations. Either that body floats, it sinks, or it submerges. So let us see when the body will sink, when the body will float, and when it will submerge. Let us see all three cases one by one. The first case is of sink. That means the object is at the bottom. Let's see, density of liquid is L and density of body is rho B. Here, if the body sinks, that means whenever we put the body inside the liquid, there will be two forces acting on the body. One in downward direction, that is weight of the object, and one in the upward direction, that is density upthrust force. Here we are neglecting the resistance due to the fluid. Here the motion of the body is always in the downward direction. If we increase the size of container, the body will further go in downward direction. So thus weight is greater than the buoyant force. So weight is greater than Fp. Weight is mass of body into G, and buoyant force is, just we have seen, it is the weight of fluid displaced, that is equals to mass of liquid displaced into G. This G will get cancelled out. We can write mass of body is equals to density of body into volume of body is greater than mass of liquid, can be written as density of liquid into volume of liquid displaced. Here whole object is inside the liquid, so volume of liquid displaced will be equal to volume of body. This VB will get cancelled out, so density of body is greater than density of liquid. If density of body is greater than density of liquid, then the object will sink. And here remember, the weight is greater than the buoyant force. Now let us see the second case. In the second case, the object partially floats. Let's say some part of object is inside and some part is outside. Total volume of body is VB and volume of body inside is VB dash. Now whenever any body floats on the surface of liquid, it is in equilibrium. For example, the wooden block floating on the surface of water. Even if we try to push this object, the moment you remove the external force, this object will again come to the surface. So at any point this body is in vertical equilibrium. Two forces acting are weight in the downward direction and buoyant force in the upward direction. as this body is in vertical equilibrium, we can write FB is equals to W. The buoyant force is given by mass of liquid displaced into G, and the weight is mass of body into G. Mass of liquid displaced is given by density of liquid into volume of body displaced. Volume of liquid displaced. The volume of liquid displaced is equal to the volume of body inside the fluid. Here volume of body inside the fluid is VB dash, given VB dash is equals to volume of body inside the fluid. So density of liquid into VB dash into G is equals to density of body into volume of body into G. This G will get cancelled out, so we can write density of liquid into VB dash is equals to density of body into volume of body. VB is volume of body, VB dash is volume of body inside the fluid. Rho B is density of body and rho L is density of liquid. We can write from this rho B by rho L is equals to VB dash by VB. VB dash is volume of body inside and VB is the total volume. So clearly VB dash is less than VB. So we can write density of body is less than density of liquid. Whenever density of body is less than density of liquid, the body will partially float. Now let us see the third case, that is the case of submerge. The submerge means the body will just float below the surface of water. So it will float like this, just below the surface of water. Even if we push this object in downward direction with some force and move it at this point, the moment we remove external force, it will not go further down or further up. It will be at that point only. So we can say that this body is at equilibrium at any point inside the fluid. The force acting in downward direction is W. Force acting in upward direction is buoyant force FB. At any point it is in vertical equilibrium, so we can write weight is equals to buoyant force. Weight is density of body into volume of body into G, and buoyant force is density of liquid into volume of body inside. Here complete body is inside the liquid, so volume of body inside will be VB into G. This VBG will get cancelled out, so we can write density of body is equals to density of liquid. If the density are same, then we will get the case of submerge. We can see this in practical life. If we fill a plastic bag full of water, there should not be any air gap. Tie it and put it in the water. It will just float below the surface of water, as the density inside the polythene and density outside the polythene is same. It will submerge. Now whenever body is fully or partially immersed in a fluid, it will experience an upthrust. So for body, the force in downward direction will be mg and force in upward direction will be buoyant force. So net force in downward direction will be mg minus buoyant force. This is called the apparent weight. of body inside the fluid. If we know the weight of body in air and weight of body in water, let's say WA is weight in air and WW is weight in water, then relative density of body is weight in air upon weight in air minus weight in water. If WL is the weight in unknown liquid, then relative density of that liquid is equals to weight in air minus weight in liquid divided by weight in air minus weight in water. These are very frequently used formulas for the numerical purpose. Now, using the Archimedes principle, we want to check whether there is cavity inside the solid looking body or not. For that, first we will measure the weight of the object in air using the spring balance. Let's say weight in air is WA. Now we have immersed the body completely inside water and measured the weight in water, that is WW. The upthrust will be weight in air minus weight in water. Now, let us assume that there is a cavity inside the body. There are two different things, two different volumes. One is called solid volume and one is called outer volume. So V solid and V outer. For example, take this pen. It is made up of plastic. The amount of plastic used to make this pen is called V solid. But the shape of this pen is cylindrical. If we find the volume of this cylindrical shape, that is V outer. It is not necessary that the amount of plastic used in the pen is same as its outer volume. If both the volumes are same, then it will be completely solid body. So we will find the solid volume, we will find the outer volume, and we will check whether solid volume is greater than outer or it is less than outer or equal to outer. To find the solid volume, we are given three things: weight in air, weight in water, and density of body. So V solid will be weight in air divided by density of body. Now V outer will be the volume displaced by the body will be equal to the volume of its outer surface and not the volume of the solid portion. If we dip a balloon and a solid sphere having same radius, then they both will displace same amount of water as their outer volumes are same. So the upthrust is due to the outer volume and not due to the solid volume. So the outer volume of the body will be equal to upthrust, that is weight in air minus weight in water, divided by density of water. From the given data, we can find the solid volume and the outer volume. If V solid is less than V outer, that means outer volume is more, but the solid used in making the object is less, then there is cavity. And volume of cavity will be V outer minus V solid. But if V solid is equal to V outer, then no cavity, so volume of cavity will be 0. So condition for cavity is V solid should be less than volume of outer part. Let us see one example. A solid body floats in water, has 1/5 of its volume immersed in it. What fraction of its volume will be immersed if it floats in a liquid of specific gravity 1.2? The meaning of specific gravity is the relative density. For the first case, it is floating in water with 1/5 of its volume immersed in it. So we can say VB dash is equals to VB by 5. For the case of flotation, we know the relation as density of body upon density of liquid is equals to VB dash upon VB. But VB dash upon VB is 1 upon 5. Density of liquid in CGS is 1. So density of body is equals to 1 by 5 gram per centimeter cube. Now in case 2, it is kept in a liquid of specific gravity 1.2. As the density of body is 0.2, it will float in this liquid again. So density of body upon density of liquid is equals to VB dash upon VB. Density of body is 0.2 divided by density of liquid is 1.2. So VB dash upon VB. So VB dash is equals to VB by 6. So it will float by keeping 1/6 of its volume immersed. In this example, a metallic sphere weighs 35 gram in air and 28.5 gram in water. We want to find its relative density and its weight in a liquid of relative density 0.9. First, let us find the relative density of body. The relative density of body is given by weight in air upon weight in air minus weight in water. Weight in air is 35 gram divided by 35 minus 28.5. So this will be 35 divided by 6.5. Simplifying this, we will get relative density of body as 5.4. So density of body will be 5.4 gram per centimeter cube or 5400 kg per meter cube. Now we want to find its apparent weight in the second liquid. The apparent weight will be equal to weight in air minus weight lost in liquid. So that will be weight in air minus 6.5 into 0.9. That will give us the answer 29.15 gram. In this example, a piece of gold weighs 50 gram in air and 45 gram in water. If there is cavity inside the piece of gold, then find its volume. Given the density of gold is 19.3 gram per cc. First, we will find the solid volume. V solid will be equal to weight in air upon density of body. Weight in air is given 50 gram divided by 19.3 gram per cc. So, solid volume will be equal to 2.6 centimeter cube. Now, let us find the outer volume of body. Outer volume will be weight in air minus weight in water divided by density of water. Density is taken in CGS, so density of water will be 1. So this will be 50 minus 45, that is equals to 5. As V outer is greater than V solid, there is cavity inside, so volume of cavity will be V outer minus V solid, that is 5 minus 2.6, that is equals to 2.4 centimeter cube. In this example, an alloy of zinc and copper weighs 16.8 gram in air and 14.7 gram in water. If relative density of copper and zinc are 8.9 and 7.1 respectively, then we want to find the amount of zinc and copper in the alloy. Let us say there is m1 gram of copper and m2 gram of zinc. So volume of copper, let's say V1 is equals to m1 upon 8.9 centimeter cube, and volume of zinc, that is V2, is equals to m2 upon 7.1 centimeter cube. Its weight in air is given. Total volume will be V1 plus V2, that is m1 upon 8.9 plus m2 upon 7.1. Now, loss of weight in water, that is weight in air minus weight in water, is equals to upthrust due to water. So 16.8 minus 40.7 is equals to, upthrust will be equal to volume of body inside, that will be total volume, into volume of density of liquid, that is 1, into G. This G will get cancelled out. So simplifying this, we will get 2.1 is equals to m1 upon 8.9 plus m2 upon 7.1. Also, it is given that weight in air is 16.8, so m1 plus m2 is equals to 16.8 gram. From this two equation, we can find m1 is equals to 9.345 gram and M2 is equals to 7.455 gram. So this will be mass of copper and this will be mass of zinc. In this example, a solid hemisphere of radius r is immersed into a liquid of density ρ. We want to find the force exerted by liquid on the curved surface. Here, the force on the curved surface is P naught pi r square because it is the pressure due to atmosphere plus its weight. So F will be equal to P naught pi r square plus pi r square into 2r, that is curved surface volume, plus 2 by 3 pi r cube into rho g. So force will be P naught pi r square plus 8 by 3 pi r cube rho g. So this will give us the answer. Force is equals to pi r square into P naught plus 8 by 3 r rho g. This will be our answer. Now let us see some important points about buoyancy and pressure. For the liquid, free surface is always horizontal. And let us see the other cases when the container containing liquid is moving. The first case in which it is moving vertically. Let's say this is a container which is moving vertically. The first case, it is moving vertically upward with acceleration a1. For simplicity, we will apply pseudo force. So give acceleration of equal magnitude opposite in direction, a1 in downward direction. So net acceleration in downward direction will be g plus a1. So the pressure difference between 2 points will be P1 minus P2 is equals to rho g plus a1 h. And if we want to find the buoyant force, that will be equal to m into g plus a. The second case, the whole container is moving downwards with acceleration a2. Again, for simplicity, we will apply pseudo force in upward direction. So acceleration a2 in upward direction. So downward direction acceleration g, upward direction acceleration a2. So net acceleration in downward direction will be g minus a2. So the pressure difference P1 minus P2 will be equal to rho g minus a2 into h, and the buoyant force will be m g minus a2. If the whole container is moving with constant velocity, then pressure will be same, rho g h, and buoyant force will also be same, m g. In case of free fall, it is moving downward with acceleration a is equals to g. So the pressure difference will be equal to rho into g minus g into h, that will be equal to 0, and b is equals to m g minus g, that will also be 0. So in the case of free fall, pressure at all the points will be same and the buoyant force acting on the object will be 0. Now, what will happen if the container is moving horizontally with some acceleration a? Let us consider 2 points A and B. If this container is moving in this direction with acceleration a, due to inertia of rest or inertia of motion, the liquid will appear to be like this, making some angle with the horizontal. Let's say this angle is theta. We are considering 2 points A and B. The height of liquid above point B is h2, and height of liquid above point A will be equal to h2 plus h1. Let's say the horizontal distance between A and B is L. The pressure difference between A and B can be given by PA minus PB is equals to rho G H2 plus H1 minus rho G H2. So that will give us answer rho G H. Rho G H2. Now, in this triangle, this height is taken H1 here. In this triangle, we can write tan theta is equals to H1 upon L. Now, in the case of the pressure difference along horizontal, we can write PA minus PB is equals to rho L A, because tan theta is equals to H1 by L, that is equals to A by G. So PA minus PB can be written as rho LA, or PA minus PB is written as rho GH2. Here A is the horizontal acceleration and L is the horizontal distance between A and B. G is the vertical acceleration and H2 is the vertical height difference between A and B. Now in this case, a U-tube is moving. The distance between two arms is L. It is moving horizontally with acceleration A. The height difference between two levels in the two arms is h. From this we can write tan theta is equals to h by L, and that is equals to A by G. Given the length between, or the distance between two arms, we can find the height difference between the levels. Now let us see one example based on this. An open tank of square base of side 4 meter and height 3 meter contains water up to height of 2 meter. Now it is horizontally accelerated. Find the maximum acceleration so that water does not spill, and if acceleration is further increased by 60%, calculate the volume of water spilled over. First, let us calculate the maximum acceleration. Let's say if it is moved with A max, then this maximum height should be equal to 3. This is y and this base is 4. Let's say this angle is theta. We can write tan theta is equals to A by G. Here it is the maximum acceleration, so that volume does not change as water does not spill. So volume of this should be equal to volume of water before it was accelerating. So half into, this is the trapezium, sum of parallel sides into perpendicular distance between them, that is equals to initial volume of water 4 into 4 square area, and it was filled up to the height 2. From this we can find y is equals to 1 meter. Tan theta is equals to a max upon g. If this height is 1 meter, then this height will be 2 meter. So a max upon g will be equal to 2 by 4. So a max will be equal to g by 2. Now in the second case, it is increased by 60%. So a will be 1.6 of g by 2. That will be 8 meter per second square. So tan theta will be equal to a by g, that is equals to 0.8, and tan theta can also be written as 3 by x. Here x, as water starts spilling, it will lose contact from here. This point is x and this angle is theta. So 3 by x is equals to 0.8. So this x will be equal to 3.75. So the volume of water spill is equals to half into base is of 3 into 3.75 into 4. So this will give us the answer 22.5 meter cube. This is the water remained. So water spilled is equals to total volume, that is 32 minus 22.5. This will give us the answer 9.5 meter cube. Now let us see the change in water level when a solid body is dropped from a boat into the water. There is a boat, it is floating on a surface of water with a body of mass m inside it. Now we have dropped this body into the water. What will happen to the water level? It completely depends on the density of this body. Let rho s is the mass of body, capital M is the mass of boat, and small m is the mass of body or object. Here we can write buoyant force is equals to m plus m into g. So V1 rho water into g is equals to m plus m into g, because it is floating. So buoyant force and weight will be in equilibrium. From this we can write V1 is equals to m plus m upon density of water. Here V1 is the volume of boat immersed initially. Now if it is given that density of solid is greater than density of water, then body will sink once we drop it from the boat and displaces a volume of water equal to its own volume. So volume of water displaced will be equal to m by density of water plus m by density of solid. Here density of solid is greater than density of water, so V2 will be less than V1 compared to this. As V2 is less than V1, the level of water falls. In the second case, if density of solid is less than or equal to density of water, then body floats and displaces volume of water equal to weight of the body. So, in this case, the net volume of water displaced will be equal to mass of boat upon density of water plus mass of solid upon density of solid. So in this case, V2 dash will be equal to V1. So the water level remains same. In the next case, a piece of ice floating in a liquid of density rho L melts completely. Now, if density of liquid is greater than density of water, then the situation will be the melted ice water will float on the surface of liquid. So in this case, the liquid plus water whole fluid level will rise. Now, if density of liquid is less than density of water, then initially it was displacing more liquid, so volume displaced was more. Now, after melting, the water level will fall. If density of liquid is equals to density of water, for example, it is floating on water only, then the level will remain same. The next case is when a piece of solid embedded in ice block which floats in water. When ice melts completely, the level of water will remain same if density of solid is less than density of water, and it will fall if density of solid is greater than density of water. Now, a liquid in a vessel is rotating about some axis. We want to find the pressure difference on different points due to this rotational motion. Initially, this surface at rest would have been horizontal, but due to rotation, the surface level at the height will at the sides will increase, and due to this there will be some pressure difference. So let us consider a cylindrical vessel rotating with constant angular velocity omega about its axis. A liquid of density rho is partly filled in the vessel. The vessel is not completely filled. Considering a small cylindrical element of length dx at a distance of x from the center, in inertial frame, the acceleration of this element will be omega square x, that is centripetal acceleration. The necessary centripetal force is provided by the pressure difference, that is P plus dp into a minus pa is equals to a dx into rho omega square x. From this we can write dp is equals to rho omega square x dx. So dp is equals to rho g dy. dy is the difference in vertical height and dx is the difference in the length. From this too we can write rho g dy is equals to rho omega square x dx. So dy by dx is equals to omega square x upon g. The slope of the free surface of liquid increases with distance from axis. So taking origin at free surface and integrating both the side, we can write integration dy limits from 0 to y is equals to integration omega square x upon g limits from 0 to x. This omega square and g are constant, so we can write y is equals to omega square by 2g into x square. So free surface of liquid is in parabolic shape, that we can see. In this case it is in parabolic shape because y is proportional to x square. Now pressure at point A, let's say this is parabolic shape, this is point A and this height is y. So pressure at point A is P naught plus rho g y, which can also be integrated. So PA is equals to P naught plus rho omega square x square by 2. So this shows that pressure at point A increases with distance x from the axis, where x distance is the horizontal distance from the axis. So pressure at point A is function of x. Now let us see the apparent weight of body and liquid in different cases. Let's say rho L is the density of liquid, rho B is the density of body. Here density of body is greater than density of liquid, so this body will sink. The apparent weight will be same as the tension force in the string. The force in downward direction will be mg and force in upward direction will be buoyant force and tension force. The tension force can be written as mg minus the buoyant force. Mg is density of body into volume of body into g minus buoyant force is density of liquid into volume of body into g. So the tension force will be rho b into vb g minus rho l into vb g. Taking this vbg common, density of body minus density of liquid. Now if this whole system is kept in an elevator and it is moving upward, with acceleration a1, then we will apply pseudo force in downward direction. System is moving upward with acceleration a1, we will apply same acceleration in opposite direction a1. So the net acceleration in downward direction will be G plus A1. In that case, apparent weight or the tension will be VB into G plus A1 into rho B minus rho L. If the whole system is moving downward with acceleration A2, then we will apply pseudo force in opposite direction, that is in upward direction. So the net acceleration in downward direction will be G minus A2. So the apparent weight or the tension force will be VB into G minus A2 into rho B minus rho L. If it is moving upward or downward with constant velocity, there will be no acceleration except the gravitational acceleration. So the tension force will be same, volume of body into G into rho B minus rho L. Now let us see some example based on Archimedes principle. A wooden block just floats inside water with a 200 gram mass placed on it. It just floats, that means it was in the condition of submerged when we have put a mass of 200 gram. Now when the mass is removed, the cube floats with its top surface 2 meters above the water level. So without mass it will float like this, and this surface will be 2 centimeter height. What is the side of the cube? Here the wooden cube's tendency was to float, but due to the additional force applied by this mass, it was submerging. So the additional volume immersed is equal to the mass. Here remember, if the liquid is water, then for water density and volume are numerically equal, not dimensionally, they are numerically equal in CGS, because density of water in CGS is 1 gram. Density is equals to mass upon volume. Density is 1, so we can write mass is equals to volume. We have placed 200 gram of water. The additional mass we have kept of solid object, that is 200 gram. So that will be the amount of water displaced in centimeter cube. Now the amount of water displaced is equals to amount of volume inside, but these are additional due to this object. So 200 will be equal to the additional volume immersed of the object will be, area will be side square, that is L square, into additional height 2. So L square will be equal to 100. So L will be equal to 10 centimeter. So side of the cube will be 10 centimeter. In this example, a body of density rho is dropped from rest from height h into a lake of density sigma. Given sigma is greater than rho, that means density of liquid is greater than density of body. So the tendency will be to float. Neglecting all other dissipative forces, that means we don't have to consider the fluid friction. What is the maximum depth up to which the body sinks before returning to the surface? Now, let us understand the situation here. This is liquid of density sigma. A body of density rho is dropped, that means initial velocity is 0, from a height h above the surface of liquid. Now, while it reaches the height h, it will have some velocity. Let's say that velocity is v1. The actual tendency of the body is to float, but due to this additional kinetic energy, it will try to penetrate and it will move further downward in the fluid. Now, once it enters inside the fluid, there will be two forces acting on the object. One, that is mg in downward direction, and the other, that is upthrust. Due to this, there will be retardation of the object. Gradually, the velocity will become 0. We want to find the maximum depth up to which it has reached. First, let us find the velocity v1. v1 square is equals to 2gh. So v1 is equals to under root 2gh, as u is 0. Now, once the body enters inside the fluid, there will be two forces, weight in downward direction and upthrust in upward direction. As this body has density of liquid greater than density of body, the upthrust will be more than mg. So net force in upward direction will be upthrust minus mg, that is equals to density of body u into volume of body vb into g minus density of body into vb into g. The density of liquid is given sigma into vb into g minus rho vbg. Taking vbg common, sigma minus rho. This is the net force in upward direction. Due to the net force in upward direction, we will get some retardation. A is equals to F net upon mass. So F net upon mass. Mass can be written as density into volume. Density of body is rho into Vb. So retardation will be Vbg into sigma minus rho divided by Vb into rho. This Vb will get cancelled out. So G into sigma minus rho divided by rho is the net acceleration. Now let us say it is going up to maximum depth d. So after reaching depth d, its velocity will be 0. So using the third equation of motion, v square is equals to u square plus 2as. V is 0. U square will be v1 square, that is 2gh is equals to 2 into acceleration is g sigma minus rho divided by rho, and the maximum depth is d. This 2 will get cancelled out, g will also get cancelled out. So we will get d is equals to rho h divided by sigma minus rho. This is the maximum depth up to which it will penetrate. After that, the buoyant force will be dominated and it will again move upwards. In this example, a metallic sphere weighing 3 kg in air is held by a string so as to completely immersed in a liquid of relative density 0.8. We want to find the tension in the string. If this is body, there will be gravitational force in the downward direction and upthrust in the upward direction. That will be equal to Fb. It is held by a string. We want to find tension in the string. So tension will be equal to, or we can write tension plus Fb will be equal to mg. So tension will be equal to mg minus buoyant force. Mass of the body is 3 into g minus buoyant force will be density of liquid, that is 0.8 into 1000 kg per meter cube into volume of body. Density of body is equals to mass upon volume. So volume of body will be equal to mass upon density. So that will be 3 divided by relative density is 10. So density will be 10 into 1000 into g. This 1000 will get cancelled out. This 10 will also get cancelled out. So tension force will be 30 minus 2.4. So T will be equal to 27.6 Newton. In this example, an object suspended by a wire stretches it by 10 mm. When the object is immersed in a liquid, the elongation in the wire reduces by 10 by 3 mm. What is the ratio of relative densities of object and the liquid? Here, the delta L is given by force into length upon area up to Young's modulus. Here, the length, area and Young's modulus will be constant. So we can write delta L is directly proportional to F. So delta L1 is directly proportional to weight in air and delta L2 is directly proportional to upthrust, that is weight in air minus weight in water. Taking the ratio, we can write 10 divided by delta L2 will be 10 minus 10 by 3 is equals to weight in air mg upon weight in air minus weight in water, that is mg rho divided by sigma. So 1 upon 1 minus 1 by 3 will be equal to 1 upon 1 minus rho upon sigma. So 1 minus 1 by 3 is equals to rho upon sigma. So we can write rho upon sigma is equals to 1 by 3. So this will be our answer. Now